All right, y'all, it's Barry. I'm here today to give you a quick summary on our sixth unit for this class, AP Physics 1. This is simple harmonic motion and waves. So we're going to run through it quickly here, get you a summary of everything we've covered to this point. Let's get right to it. First thing, we need to define what a wave is and kind of look at the properties of a wave. You see there's two types of waves. You see transverse listed up here, and the other one is longitudinal down here. And this does kind of a comparison, so we're going to start up here at transverse. Transverse is your basic type of wave that you think of. A sequence repeating over and over again is really what it comes down to. The peak and the trough move up and down above the rest position some distance based on the amplitude. A wavelength is the equal distance between cycles, and it can be found in numerous spots. So I really like this image because it shows that it's peak to peak, or same position on the rest position from one spot to the other. And that means it's going down here and passing it, and going down there and passing it, not going up in this position here. Or it's trough to trough. And in the end, what really matters is it's one full cycle. And that will be defined as our wavelength. Now, we come down here, we see a longitudinal wave. And this is something where energy is transferred in a different way. It's in the same direction as the wave velocity. We'll get to that in energy transfer in just a second. But we have our compressions and rarefactions as opposed to peaks and troughs. But they match up pretty much the same way. And you see then how that's happening, right? Up at the point where there would be a peak in a transverse wave, we have a compression, and where there'd be a trough in a transverse wave, we have a rarefaction. Wavelengths are still going to be the same thing, the distance here from the center point of a compression to the center point of a compression, or we can look at the center point of a rarefaction to the center point of a rarefaction. In both cases, the velocity here is going to be measured by the frequency, by multiplying the frequency times the wavelength. We could still take the wavelength and divide by the period, which is the amount of time for one wave, because we know velocity is distance divided by time, meters per second, but more often than not, you're going to see frequency and wavelength when you're looking at waves as far as the velocity of them. All right, now energy as it's transferring in waves. Waves transfer energy, not matter. And that's really important. They send energy through a system. They don't actually move matter. Well, they move matter briefly, but they don't move it from a location to another location. So when we had particle energy transfer, you had something hitting something else, and then it transferred energy on through collisions and momentum and kinetic energy and all that stuff. Well, now a wave moves through here, and it moves this particle up and down. All right, and that continues on through these different particles, but it doesn't actually move it from A to B. They stay in those same locations as you see. This moves up and down to cause a wave to be emitted, and then as that wave is emitted, it can affect this particle and have it move up and down too. Note that they are still in the same location, though. And that's true for both a transverse wave and a longitudinal wave. The difference between the two and how they transfer energy, and that's what's important here really, is that while the wave motion of a transverse wave right here is to the right, the energy that's being transferred is moving it perpendicular to its velocity. So it's moving the object up and down. Whereas with a longitudinal wave, like sound, it's actually transferring the energy left to right in the same direction then as the wave. Okay, and that's the difference between the two of those. Now, wave behavior. A couple pieces of wave behavior I want to hit real quickly. I'm going to start up here at the top. This is known as wave interference. Constructive interference is when waves overlap and cause greater waves. So you see right here, two small waves down here at the bottom. If we combine these, if we just add them together, well, the two peaks here are going to double to make a larger peak. The two troughs going to double. The two troughs here, going to double to make a deeper trough, a higher amplitude overall. And so we have what's known as constructive interference. Here we would have destructive because the positive here cancels out the negative here, and we end up with nothing. So that would be our destructive interference. Now, in different mediums, waves are going to travel differently. Okay, energy is going to be transferred differently through whatever substance it is that it's moving through, clearly. So what we've got right here is we've got a pulse going through a less dense medium into a more dense medium. First, as it hits this boundary between the two, there's going to be some amount of reflection coming back here. Some of this pulse is going to move backwards, and that's just the nature of how a wave would work through an object. Now, some of that energy is going to be transferred to the more dense medium and move on. But notice, this is not as tall as this one was. It's not as wide as that one was. So more dense means less amplitude and less wavelength. It's also going to mean a lower velocity. So as a wave transfers from a less dense to a more dense material, the amplitude, the wavelength, and the velocity will all decrease. All right, now the first example here of our simple harmonic motion is the simple pendulum. And a pendulum is an object, just some object, mass right here, attached to a string that will oscillate back and forth. The reason that we do these together in my class with simple harmonic motion and waves is because if we were to make a graph of this motion as it went back and forth, it would look just like a wave. It would look like a transverse wave, a sine or a cosine graph. That's exactly what we'd be looking at. Now, an important piece here is that the acceleration is always going to be at a max at its highest point and return it to the medium, where it's going to, the mean here in the middle, excuse me, where it's going to have no acceleration, and then it's going to build back up in this direction as it moves the other way. The important piece that we want to make sure we take from this is how to calculate the period. It's going to be 2 pi times the square root of the length of the pendulum from where it's attached to the center of mass, divided by gravity. Now, luckily for us, we don't really set up pendulums on other planets or in space or things like that. So for the most part, this is going to be 9.8 meters per second squared. But if you did go somewhere else or you changed gravity, that would change. The next type of simple harmonic motion is going to be a spring. And there's 2 ways to look at springs, and I want to make sure to highlight both. One is if we had a spring attached to a wall, we had an object that oscillated in the x direction here. Now, a spring could also be attached to the ceiling and oscillate up and down. That's a little different than a pendulum because a pendulum is driven by gravity. It needs to be attached to the ceiling. If you attach this to a wall, then you have a string laying on the ground. And that's it. It's not going to swing like a pendulum should, right? But a spring can go both directions there, the x direction and the y direction. This is going to be driven rather than by gravity, by the spring force. And so we're going to measure that here with K in our period equation. It's going to match up very closely to what the equation was for the pendulum. But in this case here, K is going to represent what was G, because the driving force goes from being gravity to being the spring force. And we have mass then that's going to be what's driven. And largely, as we know from previous units, the force here is Kx. And so how far it's moving from that rest position is going to be important here also, that delta x. All right, and that's going to be more important in finding the force that's applied here than it is in finding the period overall. All right, a couple basics about sound. Sound moves as a longitudinal wave, so it's a compression wave, okay? So the energy is transferred in the same direction as the wave is traveling. You see here, again, the transverse wave next to it so that you can see how these match up, but that's the only reason that that one's there. It will travel as a longitudinal wave. The accepted speed of sound is 343 meters per second, but I wanted to include all of these because the speed of sound will vary based on the substance that the compressional wave is moving through. All right, and you can see that it even varies in air based on the temperature here. So the hotter it gets, the quicker it will travel, and the colder it gets, the lower it will travel, or the less velocity it will have. Because it's a longitudinal wave, the closer together particles are, the higher the velocity will be, because they're closer, they are more capable of transferring the energy more quickly. So you notice here, as we get into more dense and more tightly packed solids, you're actually going to have a higher speed of sound. The speed of sound is going to be greater in water than it is in air, okay? And so those are things that maybe you've recognized in the past, but I wanted to give this whole table because I think that really helps point all that out. Now, the other piece here that I want to make sure to hit with these sound basics is a couple differences in intensity and in pitch. So intensity really is to just say, there's a letter missing there, isn't there? Apologies for that. The intensity is just to say how loud something is, so I can get much louder, and then I've upped my intensity, and that ups the amplitude there. But you see the wave still has that same distance. It would keep the same wavelength. The pitch is going to be more about the frequency. So I could talk really quick like this, or I could change my frequency, and I could change my voice and make it much lower, and that's changing the pitch, and that's actually changing the frequency of my voice, of the longitudinal wave that I'm putting out. All right, resonance. Now, this is a tough one, so we got kind of a 3-step thing going on here. So I'm going to use each of these different images to help show you exactly what's going on. We're going to start right up here, where we have just an object attached to the wall that if you went up to it and you just kind of hit it a little bit, like a doorstop or something like that, it would vibrate, right? Now, with different masses on the end, it's going to vibrate differently. It's going to vibrate at a different frequency. And we would refer to this right here and this right here as the natural frequencies of these two objects. It's going to be different for every object, okay? This is going to be more common in instruments than anything else, and that's going to vary based on the size of the instrument, the make of the instrument, the type. Is it a brass? Is it a woodwind? Do you have a string instrument? All of that's going to vary based on that, okay? And then we're going to move down here to a standing wave pattern inside of an actual instrument. This one's being a trombone. The natural frequency of a trombone, it's going to be modified by changing the length of the air column inside the metal tube. Imagine we made the bar here that's holding this mass longer. Well, that would also change the frequency here. And so that's what's happening in a trombone. And that's why the sound changes as you extend it. So we have changed the standing wave pattern that happens within the trombone by changing its shape. Now, what's really interesting and what happens here is as one object resonates, so as we were to start this moving here, or make a sound within the trombone, or strike this tuning fork right here, if it got next to a similar shape, okay, and by similar we have to say size and material and mass and all of that stuff, but the wave emitted by the first tuning fork here would move through the air and then cause this object to resonate, to vibrate as well. And that's what's really interesting here, and that's what resonance really is a natural frequency, if paired with another object with the same natural frequency, can actually transfer energy to cause the second object to vibrate without even touching it. All right, standing waves. We got to talk about standing waves real quick because I mentioned those briefly, but these are what happens within an instrument in order to cause different harmonics, or what they're referred to as here. First thing we got to hit is the difference between nodes and antinodes. So nodes are locations where a wave hits the rest position. So you see there in the middle. And antinodes would be either peaks or troughs. All right. And so standing waves are wave patterns caused by reflecting waves. And by reflecting waves, we mean they move back and forth within an object. And that's what an instrument is meant to do, right? It's not meant to send it out once and make the sound go away. It's meant to resonate, to be a standing wave within itself. And so this is most common within instruments, and it's going to be based on really how many nodes and antinodes are present. So if we don't touch any keys on a saxophone, we're going to have likely our first harmonic here. It's going to be a long wavelength because we're not closing any parts of it to keep that standing wave within it. Whereas if we were to change the keys that we were placing, we could go into the second and third and fourth harmonic, and we would change the actual length of the wave within the length of the standing wave within the instrument, and that's what would change the sound of it as well. All right, got to hit a couple of specific things that come with sound. First one here I'm going to talk about is sonic booms. This is when an object creating a sound moves faster than the speed of sound, and you get an overlap here and a cone created by the sound waves as they come out there. You can actually see this visibly in an airplane, and there's an image of that right there, and it's an overlap of that, and it causes a loud sound because you have essentially double the noise happening at the same time because of that overlap. Now, the Doppler effect is the same type idea, but we're not quite getting to the point where it's going faster than the speed of sound. And so what happens here is if you had a sound wave that was being sent out right here from this bugle or whatever the heck this thing is, if we were to move it closer to you, well, then we've got a different wave type than if we were moving it away, okay? And really, we've got a difference in wavelength and in frequency happening because of that. So here we're going to have a smaller wavelength and a higher frequency. Here, a longer wavelength and a lower frequency. And you see that up here in the ambulance as well, right? So if you're on the back side where they're more spread apart, a longer wavelength, lower frequency. On the front side, a smaller wavelength and a higher frequency. And last thing we got to talk about is the ear, and we got to do this quickly. This is something you learn more about in like a biology class, but because it's how you interpret these waves, I'm going to hit it very quickly here. So the sound wave is tunneled into your ear because of this fun little structure that we've all got attached to our heads. It moves in until it gets to your middle ear here, where you have your 3 bones all together that help it vibrate and go into your cochlea, and that cochlea then amplifies and puts it through your auditory nerve so it goes to your brain. So really what it comes down to is these little pieces here all come together to make it so you can interpret what these longitudinal waves are as they get close to you. So I hope overall that was helpful. Thanks for being here.